Hello, welcome back. This is Calculus 1, and we're working with taking derivatives. And today we'll look at the product rule and the quotient rule. So basically taking the derivatives of products of functions and quotients of functions. So first we'll take a look at products. And I want to sort of do an investigation. So let's take a look at this example. So f of x equals x minus 2 times x plus 2. Right? It's an easy example. I want to find its derivative. We can find its derivative using the techniques we already have. We can just FOIL the thing out. Right? So I'd get x squared minus 2x plus 2x is 0, and then minus 4. And then we can take the derivative. Okay. So that would just be the derivative of x squared, bring down the 2, x to the 2 minus 1 is 1, and then the derivative of constant is just 0. Right? Okay. We want to find a shortcut, kind of. Right? We're hoping that maybe, just maybe, if to take the derivative of this thing, maybe all we have to do is take the derivative of the parts. So maybe the derivative with respect to x of f of x is equal to the derivative with respect to x of x minus 2 times the derivative with respect to x of x plus 2. Okay, we don't know, but why not try it, right? Okay, so we have the answer there. We can see if this works. So here we go. F prime of x, take the derivative of the first one, the derivative of x minus 2. The derivative of x is 1. The derivative of minus 2 is 0. So the derivative of x minus 2 is 1. And then the derivative of x plus 2, what is that? So the derivative of x is 1. The derivative of 2 is 0. So what do we have for our potential derivative? 1? No, right? That didn't work. So in general, it doesn't seem that it's a universal statement, right? It's not gonna, at least we found one example where that doesn't work. So we can't say for all products of functions, the derivative of the product is equal to the product of the derivative. Maybe there exists one where that works, but at least for all of them, it doesn't work. Okay, okay. So what does work then? And it turns out it's going to be the following. The derivative with respect to x of f of x times some other function g of x is actually equal to leave f of x alone and take the derivative of g of x, and then go plus take the derivative of f of x and leave g of x alone. Okay, and we could then apply that to this function here, or at least show it works in this particular case. So the derivative of that thing, and I'm sorry about calling it f of x, I should have just called it y or something. So let's say y prime is equal to leave f of x alone times the derivative of g of x, which in this case, this guy would be like our f of x, and this would be our g of x. Let's call this guy h of x or something. Sorry, I have to go back through, put everything in the h of x. So if you take the derivative of g of x, you're just going to get 1. Right? And then plus, now you take the derivative of f of x and leave g of x alone. So the derivative of f of x is 1, and then leave g of x alone. So that's just the x plus 2 part. Okay. So what do we get? We get x minus 2 plus x plus 2. Which equals x plus x is 2x, and then minus 2 plus 2 is 0. So now, yeah, we have the actual answer that we were after. And it seems at least it works in this case. Okay, we haven't proven that it always works, right? And so in order to prove that it actually always works, we have to then go to the derivative. Okay, so, go to the limit definition of the derivative. So assuming that these functions actually have derivatives, we can go to that limit definition and rewrite things. Okay, so this is the same as the limit. This change in x goes to 0 of f of x plus. So you just put x plus change in x in the product, and then g of x plus change in x, and then minus f of x times g of x all over change in x. That's just our limit definition for derivatives. Okay. And then this next part takes a leap of imagination. Okay, it's probably not something you would think of doing, but you sat around long enough and thought about it. You know, maybe during the middle of a pandemic, you had some extra time on your hands. You probably would have figured it out. So, what is this kind of little trick that we're going to do? I'm going to subtract f of x plus change in x times g of x, and then add it in. So subtract it, and then I'm going to add it. Okay. Over change in x. And then I'm going to split it into two different limits. And it'll turn out, because we know that the derivatives of each of the functions exist, we can kind of get our answer. Okay, so first I want to take these guys and make that into basically a limit. Okay, so I'll have f of x plus change in x times g of x plus change in x minus f of x plus change in x times g of x. And you can kind of see I can factor, then my next step is going to be to factor out the f of x plus change in x, and what will be left will be the derivative of g of x. Right? And then I have plus the limit as change in x goes to 0 of f of x. So I take this other part now. You can do that with fractions. You can split them up over their common denominator. Okay. So I get I made a little mistake here. Okay. Let's go to big screen. Right, so f of x plus change in x times g of x minus f of x times g of x, and of course I'm going to factor out that g of x and that part, and I'll have the derivative of f of x. Okay, you kind of see where it's going, right? So firstly, I factor out the f plus change in x, and then I can split this into two limits, right? Limit as x goes to 0 of f of x plus change in x times the limit as change in x goes to 0 of g of x plus change in x minus g of x all over change in x, and then plus the limit, and here I'm factoring out the g of x, and then breaking it into two limits. The limit of a product is equal to the product of the limits so long as each individual limit exists. Okay, that's one of our limit laws. And then it's times the limit of f of x plus change in x minus f of x all over change in x. As change in x goes to 0, and we're almost there. So the first limit, and I'll put this part in red. This is just a substitution limit. You could substitute in change in x equals 0, and you just have f of x. Okay, so that first part is f of x. And then the second part, the second factor there is just the definition of the derivative of g of x. And although I didn't write it, I presume that f of x and g of x were differentiable. Okay, so the second part then is g prime of x, and then plus the second limit part here, I'll put it in red again. The first factor in that product and the second term of this expression is the limit of, basically with respect to change in x going to 0, it's basically just a constant. So the limit of g of x is just g of x. And then the second factor there is the derivative of f of x. Okay, it's just the limit definition derivative. So I can replace that thing with f prime of x, and lo and behold, then I've kind of proven. I should have made some explicit assumptions there, but I've proven, I think, to a reasonable extent that the derivative of the product is equal to this weird sum of quasi-products, right? Okay, so now we can apply this to anything the book is crazy enough to throw at us, right? So, for example, y equals x cosine x, right? So y prime will equal, okay, so I leave, you pretend this first guy is f of x and the second guy is g of x, right? So leave f of x alone, so I have x, and take the derivative of g of x, so that'll be negative sine x, plus, then I leave cosine x alone, right? So I have cosine x and times the derivative of f of x, which in this case is just 1. Okay, and then you'll have negative x sine x plus cosine x. Okay. Okay. You don't have to be crazy about the order. Obviously, there's the commutative laws of multiplication and addition say that this product rule thingamajig here at the top of the screen can be rewritten in a bunch of different orders here. You can go f of x g prime of x and then plus f prime of x times g of x. You can go f prime of x times g of x and then plus f of x times g prime of x. But the main thing is that first you take the derivative of 1, leave the other one alone, and then plus take the derivative of the one you did not take the derivative of before, and leave the one alone that you took the derivative of before. Okay, so that's the main thingamajig there. Okay, let's look at one more, maybe one or two more. Let's look at another example. So here we have g of s equals the square root of s times s squared plus 8. So let's say you didn't feel like foiling, or in this case distributing. You could always use the product rule, so you'll have that now in your back pocket as another tool. So in this case, the derivative is going to be s to the 1/2 times the derivative of s squared is 2s, and then plus, then I take the derivative of s to the 1/2, so bring down the 1/2, s to the 1/2 minus 1 is negative 1/2 times s squared plus 8. And then we can clean it up a bit. Sometimes a little longer. It's better just to distribute and take the derivative, in my opinion, but I don't know. So 2s to the 3/2 here, and then plus 1/2 s to the 4/2 plus negative 1/2 is 3/2, and then plus 1/2 times 8 is 4, s to the negative 1/2. I could combine some like terms here. So that's going to give me 4/2 plus 1/2 is 5/2, s to the 3/2, and then plus, if you wish, 4 all over square root s. Kind of get rid of those negative exponents, right? Okay, so that's another, let's do one more. So you can take this up a notch to products of maybe 3 functions. So here we have 2x cubed plus 5x, then times x minus 3, then times x plus 2. Okay, so in this case, you're taking the derivative of 1 and leaving the other 2 alone, and so you're going to have 3 terms in your sum. Okay, so we'll work in reverse order. Take the derivative of the last one first. Okay, so the derivative of x plus 2 is just 1, so we have that, and then plus. Now I'll take the derivative of the middle one. Derivative of x minus 3 is just 1. And then take the derivative of the first one. So what do we have? The derivative of 2x cubed is 6x squared. The derivative of 5x is 5. And then x minus 3 times x plus 2. Okay. Depending on what you need it for, you can probably leave it like that or factor the whole thing out, combine like terms. Let's not do that, though. Okay. Let's move on to the quotient rule. And again, we can play around with this notion that maybe, hopefully, the derivative of a quotient is potentially equal to the quotient of the derivatives, right? So right now we don't have a rule, but maybe that's what it is. Okay, so an example, let's say y equals x minus 2 all over x, right? So our question is maybe, just maybe, all I have to do is take the derivative of the top and bottom, right? And that will be my answer. Okay, so let's see what it actually is. I can pull this trick where I split it, and they call butterflying it. So get x over x minus 2 over x. Let's simplify that. That'll be 1 minus 2x to the negative 1. Its derivative then is going to be, okay, the derivative is 1 is 0, and the derivative negative 2x to the negative 1. Bring down the negative 1, I get 2. X to the negative 1 minus 1 is negative 2. Okay, so that's our answer. Let's see if what we get if we just took the derivative of the top and the bottom separately. So I'm saying it's the derivative of this thing is equal to just taking the derivative of the top all over the derivative of the bottom. Okay, so let's see what that is. And if we did that, that would be saying that y prime would be equal to 1 all over 1, which of course is equal to 1. And of course that's not true, right? Just comparing it to this guy, we can't say universally that the derivative of the product or the derivative of a quotient is equal to the quotient of the derivatives. There exists at least one case where that's not true. Here it is, right? Okay, so what then would be the quotient rule? And this time I'm just going to give it to you. We're not going to prove it. But it's this thing. And this thing tends to be a little harder to remember, which is good because you don't want to use it if you don't have to. Okay? It'll be g of x, f prime of x, minus then f of x times g prime of x. And this time you can't like reverse the order because of that minus sign. So the commutative law, 3 minus 2 is not equal to 2 minus 3. So you can't screw around with the ordering like you could as much with the product rule. Okay? All over g of x squared. Okay, and let's take a look at doing that problem we were just looking at, right? So if we had y equals, what was it, x minus 2 over x, and I would rather just split it into 2 and then take the derivative that way. Let's just verify that, at least in this case, the quotient rule works. So y prime would be the g of x, which is on the bottom. So this is g, and then this part up here is f. So g of x, x times the derivative of f, which is 1, minus f of x, which is x minus 2, times the derivative of g, which again is 1, all over g of x squared, so x squared. Okay. So what is this? This is x minus x plus 2 all over x squared, which is 2 all over x squared. And yeah, we got it. We nailed it, right? So that thing, I'm trying to snake my way back to the answer, is the answer. So it seems to work. We haven't proved it universally, but I'm not going to go through the proof of that thing. That's in the book. You can go ahead and read it and convince yourself. And again, I think it takes some clever little trick where you have to add and subtract something into the limit definition in order to pull it off. Okay, so let's take a look at one or two of these characters and see what's going on. Okay, so examples in order. G of t equals 3t squared minus 1 all over 2t plus 5. Okay, so I got g prime of t equals the bottom times the derivative of the top, 6t minus 0, this is just 6t, minus the top, 3t squared minus 1, times the derivative of the bottom, times 2, all over the bottom squared. There's little songs to learn this out slamming their way through the internet. What was going through the the world when I was a calc student was this phrase, low d high minus high d low. Low d high minus high d low. Okay, all over the low squared. So that's how they taught me to memorize it, and that seems to work. But my only issue is that you don't want to use a nuclear bomb every time you have a small skirmish, right? So I almost am to the point where I don't tell people the easy ways to remember it, because it makes it harder for people to remember. They're not going to use it all the time, right? So anyways, yeah, low d high minus high d low, but you know, usually you're hoping not to have to pull it out. So anyways, let's clean it up a bit. Have to distribute here, so I got 12t squared plus 30t minus, distribute here, 6t squared minus 2 all over 2t plus 5 squared. And then 12t squared plus 30t minus 6t squared plus 2 all over 2t plus 5 squared. Combine like terms, and you're always hopeful that you're going to find some simplification, but it's really not usually going to be the case. Okay, over 2t plus 5. Looks like you factor out a 2 from the numerator, but then you're never going to get a factorization with a 5 in the right position, so you can do a cancellation with the denominator. So ain't going to happen, and so you just kind of leave it where it's sitting, and that's the best you're going to make it look. Let's look at another example. Okay. So here we have f of x is sine of x over x. Okay. So f prime of x, low times the derivative of the high, minus high times the derivative of the low, all over the low squared. And then not much to do. It's just x cosine x minus sine x all over x, and you're done. Okay. They can make your life a living heck with these problems. Like the following example. It looks like it's a product times a difference time, where one of the terms of the difference is a quotient. So you're thinking, oh no, I got to do like a product rule, a quotient rule. No. Turn it into something that's a little nicer. So simplify it, right? And clearly, first off, I can simplify the insides of these parentheses by finding a common denominator here. So just multiply top and bottom by x plus 3 times x plus 3. Okay. So I have x times x plus 3 minus 4 all over the x plus 3. That's going to be, this top part is what? This top part is x minus 1. And then I can multiply in the x, right? So x times x minus 1 will give me an x squared minus x all over 1 times the x plus 3 is x plus 3. And what you end up with is just a quotient of two parts, and you could do a quotient rule on it. Okay, so try to simplify. If sometimes, you know, it's just too bad, but if you can get a simplification, your life might be a lot easier. So here we go. Low times the derivative of the high minus high times the derivative of the low all over the low squared. And then looks like we have some foiling. So 2x squared minus x plus 6x is plus 5x, and then minus 3. And then distribute this minus. So minus x squared plus x all over x plus 3 squared. Combine like terms in the numerator. 2x squared minus x squared is x squared. I got a 5x and an x, 6x, and then a minus 3. over x plus 3 squared. And then you're kind of stuck because you can't factor that numerator. As far as I can tell, you're not going to be able to factor into something that's x plus 3 times something, so you can make a cancellation. You're kind of just stuck. All right, well, let's look at maybe one more. Okay. So another example. Y, and we got some exponential stuff, of course. Every once in a while that happens. So 2e to the x over x squared plus 1. Okay. Look at it. So y prime low is x squared plus 1 times the derivative of the high. Leave the 2 alone. The derivative of e to the x is e to the x. Minus the high, 2e to the x, times the derivative of the low. Derivative of x squared is 2x. The derivative of 1 is 0. Okay, so that's all over x plus 1 squared. Then I want to simplify the numerator, so I'll distribute here. So I get 2 x squared e to the x. Okay. We want to put the constant in the polynomial in front of the exponential. And then plus 2e to the x, and then minus 4x e to the x all over x squared plus 1 squared. That's pretty much all you're going to be able to do with that guy. Can't simplify it. You can factor out an e to the x and a 2, you know. But really, I mean, why bother? Let's just leave it like that. Okay. Sometimes when you get in the context, it really helps to simplify into different forms. But if you don't know what context you're in, I mean, it becomes kind of an exercise of just for the sake of doing something, I guess. I don't know. Anyways, like I was saying earlier, don't always use the quotient rule. It's too much work. And the more work it is for us humans, the more likely that we'll make a mistake somewhere. So these next types kind of look like quotient rules, but truthfully, no. You just use the power rules. Okay? So for example, this guy right here, y equals 5x squared minus 3 over 4. Do not do the quotient rule, folks. This is just 5/4 x squared minus 3/4. The derivative, leave the 5/4 alone. Derivative of x squared is 2x. And then the derivative minus 3/4 is 0. So you end up with 5/2 x in the end, right? So you can do your simplification here, but 5/2 x. Right, so don't bring a nuclear bomb to a knife fight. Again, okay, let's try one more. Again, this kind of looks like maybe it's a quotient rule, right? But if you can get away with not doing a quotient rule, please do not do the quotient rule. Okay, so here you're going to simplify it by subtracting exponents. So you end up with 4x to the 3/2 minus the exponent from the bottom, which in this case is just 1, which is the same as 2 over 2. So I have 4x to the 3/2 minus 2/2 is 1/2. Okay. We'll look at it. So take the derivative y prime. So I have 4, leave the 4 alone, bring the 1/2 down. And then x to the 1/2 minus 1 is negative 1/2. So 4 times 1/2 is 2, x to the negative 1/2. If you want to get rid of that x to the negative 1/2, it's really the same as 2 over x to the 1/2, which is 2 over root x. Okay. Okay. So again, do not use the quotient rule unless you have to. Okay. Hopefully you'll figure that out on your own. Okay. Anyways, one advantage now is we can figure out the derivatives of the rest of the trig functions with the quotient rule, right? So note tangent of x is equal to sine of x over cosine of x. So we can take the derivative of that thing, right, using the quotient rule. You know, up to now, the only derivatives we know are sine of x and cosine x. The derivative of sine of x we know is cosine x. And then the derivative of cosine x is negative sine x. Okay, that's all we know right now. But knowing that now, we can figure out the other ones. So first, tan y prime is going to be, and now I'm thinking of it in terms of sine over cosine, y prime is going to be low times the derivative of the high. Whoops. Derivative of sine is positive cosine. And then minus the high guy times the derivative of the low guy. Whoops. Derivative of the low will be sine. Sorry. Negative sine. Let me erase that too. Gee, that looks terrible. Okay. Times the derivative of the low, which is negative sine x. Okay. All over the low squared. Okay. And of course, please note, if you've not figured this out already, cosine squared is equal to cosine like this squared. Okay. You can put the 2 in the middle there. All right, let's figure out what this is. So cosine times cosine is cosine squared. Negative sine times negative sine is plus sine squared. That's all over cosine squared. And then we have our Pythagorean identities. Cosine squared plus sine squared is 1. And then 1 over cosine squared. Well, 1 over cosine is the same as what is it? Secant. So 1 over cosine squared is just old secant squared. Okay, so apparently the derivative of tan is secant squared. And now we can give you all the derivatives and all of their tremendous glory. Right? So the derivative with respect to x of sine of x is cosine x. The derivative with respect to x of cosine x is negative sine x. The derivative with respect to x of tan x is secant squared x. And then we can also do the other ones. And I'm not going to go through them all, but the way to do it is to use their, like the reciprocal identities and the quotient identities. So for, what, cosecant x, that's the same as 1 all over sine x. Okay, so we can figure that out doing the quotient rule now. And if you go through the rigmarole, the derivative with respect to x of cosecant x is going to end up being negative cosecant x cotan x. The derivative with respect to x of secant x is going to be secant x tan x. And then finally, the derivative with respect to x of cotan x is going to be negative cosecant squared x. Okay, you have to have these memorized. There is no way you're getting out the door without memorizing these. Okay, memorize. If you got to make note cards, you're making note cards. You do what gets the job done. Think back to elementary school when you learned your arithmetic tables or when you learned your multiplication tables. How did you do it? Okay? There's a reason why we force you to kind of figure that out when you're younger, because now we need to have these memorized and we need to get them done quick. Okay? All right. So memorize them. Okay. Once you're going to memorize, you should be able to handle pretty much anything that we throw at you, like example, y equals e to the x minus cotan x, so y prime, derivative of e to the x is just e to the x, minus the derivative of cotan x is negative secant squared x, and then we don't write minus minus, we want to clean it up as a plus. We have e to the x plus secant squared x. Okay, we have, I probably already talked a little bit about finding higher order derivatives, but in general, it's introduced in this section. Okay? So first, finding higher, I talked about it a little when we were talking about the cosine and sine function, order derivatives. And it's fun to see how functions behave under taking multiple derivatives. Okay, so first off, let's take a look at this guy. Y equals, 1 over x. Okay, so take its derivative. I'm going to rewrite it as x to the negative 1. And so then the first derivative will be bring down the negative 1. I get negative x to the negative 1 minus 1 is negative 2. Okay? Then the second derivative, and I just put another prime up in the exponent for the second derivative. I'll have negative 1 from the front, the constant in front of the x, and then I bring down the negative 2, and then I have x to the negative 2 minus 1 is negative 3. Okay? And I could clean that up a little. What is it? It's 2 times 1, which is just 2, and then it's positive x to the negative 3. Y triple prime, now I bring down the 3, right? So it's 2 times negative 3 times x to the negative 4. Okay. Which we could write as negative 6x to the negative 4. And then y to the fourth is, well, I bring down the negative 4, so I'll have negative 6 times negative 4, x to the negative 5. And that's going to be 24x to the negative 5. And then you can put y to the 5. So you could also write parentheses and then the number of the derivative and the exponent. So the next exponent, the next derivative would be the fifth derivative. I have 24 times negative 5 times x to the negative 6, which is whatever that is, 120 maybe. 4 times 5, 0, 2, yeah, 120. So negative 120 x to the negative 6. And so on and so forth. So later on, they're going to be having you look for patterns, especially in Calc 2, because we can rewrite a lot of functions in terms of polynomials. It's easier sometimes to work with polynomial forms than to work with like a trig function or something. So what you do to obtain that polynomial form, which you're going to call like a Maclaurin series or a Taylor series, is take repeated derivatives. Okay, and you'll need kind of a general form for the nth term of the derivative, and usually we call that iteration. Okay, so you're iterating to find a pattern. You might not necessarily prove it, right? So factorials always come up in that context. And you kind of see how the factorials happen here, right? So 2 is really the same as 2 factorial. Let me get my pen working. So this is 2 factorial x to the negative 3. When I took the next derivative, I was multiplying by a 3. So if you don't know what a factorial is, like 5 factorial, that's 5 times 4 times 3 times 2 times 1. 6 factorial then is 6 times 5 times 4 times 3 times 2 times 1, which is just really 6 times 5 factorial, right? So when you multiply the next term, when you bring down the next term after taking the derivative, you end up with, in this third case, 2 factorial times 3, but that's really 3 factorial. Okay? So negative 6 is the same as negative 3 factorial x to the negative 4. 24 then is 4 factorial x to the negative 5. 120 is, in this case, negative 5 factorial x to the negative 6. In general, and I won't call upon you to do this in this class, but in general, the nth derivative will be negative 1 to the nth power times n factorial times x to the negative n plus 1. Okay, so that will be on the chopping block once you get the Calc 2. Okay, I think we'll leave it there, and the next time we'll have a chain rule to worry about. And thanks for watching, and I'll see you next time.